Open up Visual Studio Code, Electricity and Magnetism. Click this button, 065, Growth Shading. Click this button, Growth.cpp. Click this button, Growth.birth. Click this button, Growth.preg. Click this button, debug.txt. Click this button, release.txt. Ctrl V. I will close welcome window. In the growth.cpp, I will discuss normalized, interpolated, packed buffer, stride, offsetof, glVertexAttribPointer. In depth, I will drag and drop OpenGL Programming Guide, 9th edition. In this book, search for smoothly interpolating data. Click this button, Chapter 4, Color, Pixel, and Fragments, Buffers and their uses. Color buffers. In this part, if you scroll down, you can find smoothly interpolating data. Now I will toggle off, then arrange. Like this. I will read this part of text very carefully. Smoothly interpolating data. Let's take a closer look at specifying data with a vertex. Recall from Chapter 1 that vertices can have multiple data values associated with them, and the colors can be among them. As with any other vertex data, the color data must be stored in vertex buffer object. As data is passed from the vertex shader to the fragment shader, OpenGL will smoothly interpolate it across the face of the primitive being rendered. By using this data to generate colors in the fragment shader, we can produce smooth shaded object on the screen. I will scroll up. This is known as growth shading. In example 4.1, we interleave the vertices color and the position data and use an integer valued type to illustrate, having OpenGL normalize our values. I would highly recommend you to read this part of text very carefully. Now include CPG, SCD extensions. Include OpenGL Programming Guide 9.hpp. Begin app declaration. End app declaration. Define app. We have to provide class name growth shading. Copy this, paste it here, quote growth shading. Select debug.txt, icx.cl, growth.cpp, oi.exe, qsdd, C++20, ehsc, mdd, link, subsystem, console. If you want, you can use fno SQL. Copy, paste it in release. Now I will delete D instead O2 for optimization. In the debug.txt, remove icx.cl. In case of debug, we used D switch mdd. In case of release, we do not use mdd. Instead, we use md. Also, O2 switch. This is for release build. Now select growth.cpp. Open up this command prompt. dir cd 065 glOt shading icx cl at debug.txt, hit enter. It should build successfully. In case of release build, you can use release, hit enter. Release build should also work. Now close it. Select begin app, right click, go to definition. In this file, you can find virtual void initialize, copy up to resize, copy. In this section, public, paste. We will remove keyword virtual, replace all, close it. Override, 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 override. In the private section, private glUint program. I would highly advise you to initialize, copy. In the finalize delete program. Don't forget deleting or releasing resources after use. In the initialize, we rebuild. We are building debug build. CLS I. It crashed. Control C. The reason it crashed is that we need to call base initialize title. We rebuild CLS I. Now it should work perfectly. Don't forget calling base initialize. I will define struct Vertex data. Don't miss semicolon. Here GL unsigned byte. Color, this is array. GL float position 4. So we defined a struct named Vertex data. Now in this code we will copy this part of text. Copy, paste it here. I will arrange like this. I will give open block, closing block, indent. I will simply delete semicolon. Then scroll up, int, semicolon. In this part, size of vertices over size of vertex data. Let's try to build. If it builds, I missed semicolon here, 42. I need to delete this curly brace. We rebuild. Okay, it built successfully. Now close it. In this part, program, create program. We have glOt but, glOt fragment. So glOt but, glOt frag. Select glOt but. I will arrange side by side. Version 460 core. Version 460 core. With this, we build again. CLS I. It builds and runs successfully. Now close it. I will arrange side by side. We need to take color and the vertices. Layout, location, 0, V, color. It should be in back 4. Layout location 1 in back 4 V position. Void main we need in back 4 I say VS color or FS color. It should be output. Copy this. This will be input in our fragment shader, so it should be in out back 4 out color. Void main out color we assign FS color. Now select vertex shader, GL position V position, FS color this vertex color. We rebuild CLS it should build and run successfully. Now in the private section enum V color should come first because we set location 0 for V color. Then V position semicolon. V position is 1 for this location. To feed V color V position with data, we need glUint vertex array object. glUint. We also need vertex buffer object. Scroll down. GL create vertex arrays. 1 vertex array object. GL bind vertex array. Vertex array object. Please understand, in this shader we have 2 vertex attributes. They are V color, V position. To feed V color and V position with data from our host client app, we have to create vertex array object or VAO. So we created vertex array object. Now GL create buffers. 1 vertex buffer object. GL named buffer storage. VBO size of this vertices here. Then data vertices. Please notice this is bit field flag. Post drawing we simply pass 0. Then GL bind buffer. These vertex attributes should be mapped. GL array buffer VBO. Now we have to specify the type formats for V color. We use glVertexAttribPointer. glUint index. This index means location for V color. Its location is 0. We defined enumeration V color. We pass here. Then int size. Please note V color takes floating point back 4. Element type of back 4 are floats and has 4 elements or components of type float. In this case, this represents color. Color is of type GL unsigned byte. Each color has 4 components, so 4 type. We declared color as GL unsigned byte. Here it should be unsigned byte. Please notice we used unsigned byte because our color, the type is GL unsigned byte. Now normalize GL true. I will discuss what normalize means shortly. Then stride. We have to pass size of vertex data because this is one vertex data. This is two vertex data. From the first color to the next color, there are this amount of memory, this amount of memory in between. So this value is stride. Then GL pointer. This is offset. Offset is null. GL enable vertex attrib array. We enable vcolor. This vertex attribute array. Its location is 0, but we can use vcolor because vcolor is defined to be 0. Now GL vertex attrib pointer. We specify data format for v position. Its location is 1. So here it should come 1. But we defined enumeration v position enumerator. So we can put here instead. Then GLU int size. In this specification, we provided two values for a single vertex position, two floats for a single vertex position, but we declared array with 4 elements. If we pass 4, let's try it. Then type GL float normalized. In our position, the type is float. This is integral type. This is floating point type. In case of floating point type, we don't need normalization. We say GL pulse, then stride. From first vertex position to next vertex position, the memory gap is size of vertex data. So this stride should be size of vertex data. Then pointer. This is offset. In this book, the offset is computed like this. Size of vertices 0 color. Instead of using this, we will use offset O. We provide vertex data the structure name. Here we already consumed color. Instead, we provide position. I will make it bigger. It should be of type void pointer. Now GL enable vertex attrib array v position. I will remove some space. In the function display, GL use program static const GL float black 0 0 0 0 GL clear buffer FB GL color draw buffer 0, then value black. Now GL draw arrays GL triangles first 0 count num vertices. With this we build again. It built successfully. CLS I. it does not work. Now close it. Scroll up. We declared V position with 4 elements, but we provided 2 elements for each vertex position. Once again, we declared 4 floats, but we provided 2 values for each vertex position. In our vertex shader, here we declared back4. I fixed my wording here. Back4 has 4 elements of type float. In this case, we provide 2 values for our position. So vertex array attrib pointer for V position, we have to set 2. With this, we rebuild CLS I. It now works perfectly. I will close it. Why this is problem? OpenGL uses homogeneous coordinate system in case of floating point types such as float or double. Back4 V position, if we initialize back4, for example 1, 2, this is equivalent to back4, 1, 2, third element 0, fourth element becomes 1. This is property of homogeneous coordinate system. So in this case, for vertex position, if we provide 2 elements for V position, remaining 2 components will be filled with 0 and 1. Now I will restore it back 4. With this, we have to fill 0, 1. Copy, paste, 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 paste. If we build, it should work. CLS I. It of course works perfectly. Now close it. We used for color components. Here, color is defined with 4 elements. We can set it 3. Then this is redundant. We can delete this part like this. Now our color components has 3 elements. So for BindTextureUnit V color, we now have 3. If we rebuild CLS I, it works perfectly. Even though we provided 3 elements V color, in this case, this will be like this. V back4, we provide 3 color from CPU or host memory. This is equivalent to like this, 255, and it should be normalized, unnormalized. If it is normalized, it will become back4 from this. Here we divide like this, like this, like this, like this. Then this will become 1, 0, 0, 1. This is homogeneous normalized coordinate system. We have to understand we provided integral type for color attribute. This integral type is normalized for floating point type from our host CPU application to our Vertex shader. Then from this V color normalized Vertex color is interpolated to fragment shader. This color comes from Vertex shader, and now interpolated. If this color is not interpolated, if we build and run again, we will not have color inside these triangles. Colors inside these triangles are interpolated. Once again, from CPU host memory to GPU vertex shader, our vertex value for color is normalized. Then from vertex shader to fragment shader, this VS color is interpolated. In this book, scroll up, you have to read this text once again. Let's take a closer look at specifying data with a vertex. Recall from chapter 1 that vertices can have multiple data values associated with them, and the colors can be among them. As with any other vertex data, the color data must be stored in a vertex buffer object. As data is passed from vertex shader to fragment shader, from vertex shader vColor to fsColor through this statement. In the fragment shader, this color is now interpolated. So, as data is passed from vertex shader to fragment shader, OpenGL will smoothly interpolate it across the face of the primitive being rendered. Also, homogeneous coordinates. I would highly recommend you to read about homogeneous coordinates. Understanding these things is critical for successful OpenGL programming.